This is the second lecture from chapter 15, all about acids and bases. And this particular lecture explains why some acids and bases are weak and others are strong. At definition first, a strong acid is one that completely dissociates in water. So if I have 100 molecules of hydrochloric acid, which is a strong acid, what I will end up with once I put it in water is no intact HCl left over, but I will end up with 100 hydronium ions and 100 chlorine anions. In other words, it will exist, all of them, every single molecule I dissolve will exist completely dissociated. You will see the term strong and weak electrolyte throughout this chapter. An electrolyte is simply a solution that conducts electricity, and in order to conduct electricity, there must be freely moving ions available. And so obviously, what an acid does, then it dissociates into ions, right? As do ionic compounds. And so those are both strong electrolytes. And also for a strong acid only, since 100% of it dissociates, the original concentration of, in this case, the example I'm using, hydrochloric acid, will be the same as the concentration of hydronium ions you end up with, right? Because it's all going to dissociate and latch onto water molecules. Now, strong acids and bases, since the dissociation rate is close to 100%, the equilibrium, there's essentially no equilibrium, okay? The amount that returns to reactant is so small that it can be safely neglected. Another way of saying that is the equilibrium constant is so large, we can effectively assume there's no equilibrium, that we just have our product. One last thing about strong acids is because they completely dissociate and because the concentration of hydronium ion equals the original concentration of the intact acid, pH is really easy to find for strong acids, okay? So here's the formula we've been using for pH. And because we know that the concentration of the hydronium ion is simply the original concentration of the strong acid, then pH is simply the log of whatever the original concentration of the strong acid. Now you'll see for weak acids, it's not as straightforward. There are 6 strong acids, and you should just memorize them because every other acid, and there are tons of other ones, is weak. So as long as you remember these 6 ones, now there are some patterns that'll help you. All of the hydrohalides are strong acids except for hydrogen fluoride, which is a weak acid, and that's because the hydrogen-fluorine bond is so darn strong that it really doesn't want to give up that hydrogen ion. So that'll kind of help you remember those 3. And then nitric acid, perchloric acid, and sulfuric acid. Strong bases, similar definition. A strong base is one that dissociates completely when dissolved in water. And so again, if I were to dissolve 100 units of sodium hydroxide in water, there would be none of the original intact sodium hydroxide left, but it would have dissociated completely into the individual ions. And we would also describe strong bases as strong electrolytes because bases also dissociate to form freely moving ions, which support electricity. And similar as for a strong acid, it's safe to essentially say there's no significant equilibrium for a strong base, as there was not for a strong acid. And so another way of saying that is the K value, the equilibrium constant value for strong base is so large, there's essentially no equilibrium, no reactants left. And similar to the rationale we went through in finding pH for a strong acid, it's pretty easy to find pOH for a strong base because the concentration of hydroxide ion that is in solution actually equals the original concentration of the strong base because it all dissociates, right? So it's a 1-to-1 there. And so the formula for pOH, okay, is, I'm forgetting the minus signs there, aren't I? I think I did on the last page too. Minus log of OH concentration. And since the concentration of OH equals the concentration of the original base, the pOH is now simply log of the original base. As with the strong acids, there are 6 strong bases to memorize, and every other base you can conceive of is not strong. So again, there are patterns in here. All of the group 1A metal hydroxides, so lithium, sodium, potassium, they all make strong bases, dissociate completely in a solution. And then what I describe as the heavy group 2A metal hydroxides, calcium, strontium, barium. There's debate on whether or not calcium qualifies as a strong base. Some sources will say yes, some will say no because it's not very soluble, so not very much of it even gets dissolved in order to dissociate. But the little bit of it that does dissolve does completely dissociate. So really the only group 2 metal hydroxide that is not strong is magnesium hydroxide. Alrighty, now what is more difficult to find the pH of are weak acids and weak bases. And that is because if you have a weak acid and you put it in water, instead of 100% of it splitting up to give you the individual ions, only a fraction of it does that. So if I were to put 100 molecules of some weak acid in water, I might only end up with one of them that ionizes, and the rest may remain in the intact molecular form. And so because of that, if it's a weak acid, you don't really know what the concentration of hydronium ion is. You've got to do extra experimentation. Cannot assume that all of the original acid you put in is going to make hydronium. So that complicates it quite a bit. The equilibrium is very important. And so then how do we find pH, right? The concentration of hydronium is not equal to the concentration of the original intact acid. So this is not going to work, okay? So we need an ice table to find the pH for a weak acid, and we'll do some examples of those. So those are the definitions of weak and strong acids and base. So what makes a particular acid or base weak or strong? Why are some weak? Why are some strong? Well, I'm going to give you a couple of trends. First, I'm going to talk about binary acids, the acids that do not contain a polyatomic ion, right? So that would be, well, be a lot of the ones you can see right here, right? Hydrochloric acid, hydrobromic, etc. So look at the generic equation for dissociation of an acid. So the stronger the acid, the more product it's going to make, right? The stronger the acid, the more product, in other words, the more H3O, hydronium ion, it will make. And so what makes some acids more likely to dissociate and make more of this conjugate base. It depends on how stable the conjugate base is, right? So it's kind of like you going on an adventure, right? If you feel that that adventure is relatively safe, you're more likely to proceed, right? Well, the same thing here. If the weak acid, or if the acid knows that it's going to be stable and comfortable in this state, then it's more likely to go there. And so the more stable the anion from the acid is, that's what we call the conjugate base, right? The more likely it will be to dissociate. So what makes A minus stable? Well, look at the structure of A minus. It's got excess negative charge, right? It's got excess electrons. So what makes it more stable is a higher electronegativity. What does electronegativity mean? It means that atom has a strong attraction for extra electrons. So the more electronegative A is, the more stable it will be with a negative charge. And so now we have to think about the trend, electronegativity trend, right? So electronegativity increases going from left to right across a period, and electronegativity decreases going down. So we're just going to talk about going left to right, and you'll understand that in a couple of slides. So HF is more acidic. Hydrofluoric acid is more acidic than water. Okay, because fluorine is more electronegative, and therefore F minus is more stable. Okay, so let me say it from the perspective of water. Oxygen is less electronegative than fluorine. Therefore, the hydroxide anion, if it were to dissociate like an acid, is less stable, and therefore H2O is less acidic than hydrofluoric acid. Now, what's interesting, okay, so you're going to have to listen to this. This is probably going to blow you away. Let me erase all this junk. All right. So if electronegativity were the only factor we had to consider, then look at going down a group and tell me what you think the acidity would be if you compare, let's say, water to H2S, H2SE, etc. Well, you know that the electronegativity, is decreasing going down a group, right? So wouldn't that mean that they're becoming less acidic? Yeah, right? Because the less electronegative, the less stable the anion, less acidic. You would think that, but guess what? This is an area that's easy to get confused on. You're gonna definitely maybe want to replay this and write notes. It turns out that as you go down a group, the acidity increases. Okay, so hydroiodic iodide is a stronger acid than hydrobromic, which is a stronger acid than hydrochloric. What? Wait a minute, really? Because iodine's a whole lot less electronegative than fluorine. Why isn't it less acidic? All right, we have two competing factors when you're going down a group: bond strength versus electronegativity. So bond strength is most important going down a group, and electronegativity is most important going left to right across a period. Okay, so when you're comparing molecules, the acidity of molecules going down a group, think bond strength. Make sure you make a note of that. The weaker the bond, the more acidic. All right, the weaker the bond, the more acidic. And that makes sense, right? Because if the bond is weak, it's more likely to give up that hydrogen. It's like, okay, it's kind of, hydrogen's barely hanging on anyway, you can have it, right? So as we go to larger and larger atoms, hydroiodic acid, for example, that HI bond is quite weak. And so iodine's much more likely to just give away its hydrogen because the bond is already weakened, okay? Whereas the HF bond is so darn strong because those are smaller atoms, so they can get a lot closer together. It's so strong that it is the only weak acid in the whole halogen group. I like this pictorial. It kind of helps you visualize what's going on as far as acid strength a little bit better. So this was visualizing acid strength going left to right across a period. Now remember what matters when you're comparing molecules going left to right across the periodic table. What matters there is the electronegativity, right? So electronegativity is increasing left to right. And what happens to acidity? Acidity also increases. You can tell these are going to be conceptual multiple choice questions, right? So HF is more acidic than H2O or than NH3, right? Because F is more electronegative, and therefore F minus, right, which is the conjugate base of HF, is more stable. So again, trying to visualize the trend going down a group. So going down a group, electronegativity is not as important as bond strength. So bond strength decreases going down a group because the atoms are getting larger and farther apart, but acidity increases. I have such bad handwriting, sorry about that. Going down a group. So hydrogen iodide is much stronger acid than hydrogen fluoride because its bond is the weakest. This is, again, saying the same thing that I just did in the last slide. It's just some people respond better to tables than drawings. So obviously, as the bond strength decreases, it's that substance is going to become a stronger acid. All right, so now we're going to move on to ternary acids, those acids that contain a polyatomic ion. So basically what you have to think of for the acidity of ternary acids is it's usually, I think almost always, I can't think of an exception, that whatever stabilizes the conjugate base. So let's look at phosphoric acid versus, let's do phosphorus acid to compare it to. All right, so those are both weak acids, but H3PO4 is a stronger acid overall than H3PO4. Why is that? It turns out that if you get rid of the acidic protons, what are you left with? What are the conjugate bases here? Well, if I give up one proton for each of them, these are the conjugate bases. Which one of these conjugate bases do you think is more stable? The one with more oxygens is more stable because oxygen's electronegativity is electronegative. So the more electronegative atoms you add to the conjugate base portion, the more stable the anion is going to be and the more acidic the original acid will be. Here's a perfect example. Really all we're doing moving from hypochlorous to chlorous to chloric to perchloric is adding oxygens. And so what happens to the acidity? The perchloric, which has 4 oxygens, is the most acidic of these 4. And that's simply because the conjugate base, right, which is what's left over when you donate the proton. The conjugate base is the most stable of these. Now, another kind of interesting correlation is, what if you have an acid? So we'll just take this strong hydrochloric acid example. And we know that the chloride ion is the conjugate base, right? And conjugate acids and bases are literally what they're described as. They can function as an acid or a base if you were to take the reaction in the reverse, which we will be doing once we get into acid-base equilibrium. So what is the reverse reaction of hydrochloric acid dissociating? Well, it's the reaction I've shown right below it, right? So theoretically, the conjugate base of hydrochloric acid, the chloride ion, can act as a base. What does a base do? It accepts a proton, right? Simply the reverse of the top reaction. It would theoretically regenerate hydrochloric acid. Now, I say theoretically because it turns out there is a relationship. The stronger the original acid, the weaker its conjugate base. In other words, the less basic its conjugate is. Likewise, we could say the weaker the original acid, the stronger its conjugate base is. So, going back to our HCl example, if we start with a strong acid, the conjugate base we get should be weak. And the stronger the original acid is, the weaker the base it forms, or the conjugate base it forms is. And as a matter of fact, chloride is such a weak base that it in water effectively doesn't act like a base at all. This does not happen. Okay? And the reason, so listen very carefully, the reason it doesn't happen will make total sense. Because if it did happen, if chloride did in fact pick up a hydrogen ion from water and regenerate HCl, guess what? That does not exist in water because it's a strong acid. Remember the definition of strong acids and base? They don't exist as intact molecules in water. They 100% immediately dissociate into the individual ions. So this bugger doesn't exist in water, so this whole thing is not going to happen. So another way to kind of visualize that is look at the chart over to the left. The strongest acids are at top, and the weakest acids are to the bottom. And look at their conjugate bases. These are the conjugate bases on the right. So the stronger the acid, the weaker its conjugate base, the less effective its conjugate is as acting like a base. Now, talking about weak acids and bases, which we'll spend quite a bit more time on than strong acids and bases, because strong acids and bases are easy to work with. It's easy to calculate their pH because they totally dissociate. And of course, with weak acids and bases, we need an ice table. So how do we quantify the strength of an acid or a base? Well, we use the equilibrium constant. So here's the generic equation for an acid, and here's the generic equation for a base in water. And so the equilibrium constants for an acid or a base, called Ka, Kb, are shown right here. Notice that water is left out of both equilibrium constant expressions because water is a liquid. Liquids and solids are left out of the equilibrium expressions. So what is the relationship between Ka and Kb? Well, let me show you firsthand the relationship between Ka and Kb. Ammonia, as with most neutral nitrogen-containing compounds, is a weak base, and so what do bases do? They pick up hydrogen ions from acids, and so if we were to label this equation, Right, and the K, since we're talking about a base here, the KB expression for this reaction, products over reactants, leaving out water because it's a liquid. All right, so now let's look at the Ka expression for the conjugate acid formed here. So of course an acid is something that donates a hydrogen ion. So I want you to notice it's not exactly the reverse of the top reaction, right? Okay, because KB is not reacting an acid with hydroxide, it's reacting an acid with water. So just make note of that. So again, if we were to label this equation, and the Ka expression for the ammonium ion products over reactants, leaving water out again. Alrighty, so now what is the relationship between the expression for Ka and Kb? I want to show you what happens mathematically when I multiply Ka times Kb. So let's see, here's Ka. And I'm going to multiply it by Kb. Okay. Does anything cancel out when I multiply this? Look what's the same. The NH3s can cancel out and the NH4s can cancel out. And all we're left with when we multiply Ka times Kb is hydronium ion concentration times hydroxide concentration. Does that look familiar to you? Does anybody remember what we called that? That is called Kw. Pretty cool, huh? So if we have Ka or Kb, we can easily find the other one simply by using this formula. Here's an easy example just to show you the type of problem you might see that relates Ka and Kb. So you're given the chemical equation for the weak acid, nitrous acid. Now, again, you need to memorize the strong acids, but you might remember that nitric acid was strong, but nitrous is not. Okay, so here's a weak acid. So you're going to frequently see the equilibrium signs for weak acids, and a lot of times for strong acids, you'll just see one arrow pointing to products. So the Ka, they gave you the Ka for this nitrous acid and asked you to calculate Kb. Easy peasy, okay? So not that you need to be able to write out the chemical equation for Kb for this problem. They didn't ask you to do that. But I've noticed frequently that students get mixed up in how to write Kb because they want to just make it be the reverse of Ka, and it's not. So I want you to compare how these are different here. So Kb, or the base expression to get Kb, you do start with a conjugate base, okay, but you don't react it with the other product. You react it with water. All right, so anyway, back to the point of this problem. Kb, if you need to find Kb or Ka, it's simply Kw divided by the other one. Kw, unless you're told otherwise, it's usually assumed it's room temperature, 25 degrees. And so again, please make sure you're using your calculator right with scientific notation. So that's worth punching that into your calculator. Make sure you get an exponent of minus 11. If you don't, you're probably using your calculator wrong. So, and that's it for the sample problem. There's quite a strong one, okay? So let me just write it again here. Ka times Kb equals Kw. So let's say that we had Ka and we wanted to find Kb. We would simply rearrange this. Kw over Ka equals Kb. Remember that Kw, the most common value for that you'll see is at room temperature, and it's 1 times 10 to the minus 14, right? Alrighty, so another little term you're going to see is pKa and pKb, and you may remember me telling you at some point that P for chemists means minus log of something. So pKa means minus log of Ka. And again, we use the pKa versus Ka, just it's easier. If you have a Ka of 1.67 times 10 to the minus 21, it's a lot easier to write that, take the log of that, right, and write it as, I don't know what this would be, what, 20.8 something, right, than the scientific notation. And so the same type of relationships go. If you you can find the pKa by taking the minus log. If you need to go in the other direction, if you're given the pKa and you need to find Ka, it would be 10 raised to the minus pKa. Same type of equations, formulas that we used for pH. And same type of relationship. The larger K is, the smaller pKa is, okay? So if K is 1 times 10 to the minus 15th, for example, what would pKa be? Well, remember log is just taking the exponent, so pKa would be 15. Okay, so for a very small K, that means if something isn't very acidic, it's going to have a high value for pKa. And if you have a large K, let's look at a large K. 1 times, let's go the other direction, 1 times 10 to the 15. The pKa would be minus 15. So if you have a really large K, you're going to have a very small pK. Same thing with pH. One of the things that's easy to get mixed up is pH and acid strength, okay? pH is not the same thing as acid strength. So remember what acid strength is. That simply tells you how thoroughly an acid dissociates into the ions in water. pH does not tell you anything about how much of an acid dissociated in water. It simply tells you what the concentration of hydronium ion is. And the higher the concentration of hydronium ion doesn't necessarily come from a strong acid. It could come from lots of weak acid being dissolved in water. So just keep in mind that pH is not the same thing as acid strength. Kind of some food for thought here. Would you be able to answer these questions and explain them? Would it be possible to make an acidic, low pH solution? So let's say pH of 1, that's our stomach acid, is that acidic? From a weak acid? Or do you need a strong acid to do that? And why? Could you explain that? You should be able to. It turns out that yes. Okay, I could take any weak acid. Could take a super weak acid and add simply lots of it to water, and I could still get a really low pH. Right? So remember that pH just tells us about the concentration of hydronium ion, not how the hydronium ion is made or what it's made from. A similar, easily confused concept is just because an acid is strong, okay, so let's use hydrochloric acid in water, doesn't mean that the solution of acid it makes is concentrated, right? So being concentrated is not the same thing as being strong, because I could add a very small amount of a strong acid to water, And it's a strong acid, but I would end up with a dilute solution of it, so it really wouldn't be that dangerous. Okay, so just make sure you understand the difference. And the question here is, if I gave you these 4 images without the descriptors on the bottom, would you be able to describe each one? So let's look at them for a minute. Let's look at the first one. What you should be able to glean from this first one is that this is a weak acid, because I'm seeing a lot of intact HA molecules. And remember, what does a strong acid do? A strong acid completely dissociates. You wouldn't see any of these intact original water molecules left. So, but because they're even though it's a weak acid, there are a ton of them dissolved. So it's a concentrated weak acid. Look at the second picture. Every single original acid, HA, has dissociated into the individual ions. So I know right away this is a strong acid. And it's also crowded. There are also a lot of them. So it's also a concentrated solution. The third one, it's definitely a weak acid because most of them are intact molecules that haven't ionized. And it's also dilute because there aren't very many. And finally, the one on the right is clearly a strong acid because it's dissociated, the ones there are, but there's not very much there. So it is also a dilute solution. It's a dilute solution of a strong acid. And that is it for the second lecture in Chapter 15.